magistral. Quiero presentar rápidamente a las autoridades que están con nosotros y también al ponente. Primeramente agradecemos la presencia del maestro en Ciencias, Iván Giovanni Mozo García, subdirector académico. Gracias, maestro. Y bueno, al maestro y también coordinador de esta plática, el doctor Genaro Juárez. Y también agradecemos la presencia desde la República Checa del maestro Iván Zelinka. Y le cedemos la palabra al maestro Iván Mozo García para que dé la presentación del ponente.
Muchas gracias. Buenas tardes a todos. Bueno, para que, como conocen o como saben, esta conferencia del doctor Zelinka va a estar dictada en inglés. Vamos a pasar a ese idioma para justamente hacer su presentación y que también comience justamente con la conferencia. Good afternoon, everybody. This is my pleasure to welcome you all to this conference here at the SCOM. To start off, I would like to introduce our distinguished speaker, the Professor Iván Zelinka. Professor Zelinka is currently working at Technical University of Ostrava in Czech Republic. His expertise and dedication in the field of artificial intelligence, unconventional computing, robotics, evolutionary algorithms, and cybersecurity made him a renowned figure in the field. Before his academic career, Professor Zelinka gained extensive experience in technology and banking sectors, working as a telecom technician, computing specialist, and lay supervision in a commercial bank. He has been invited to lectures at several universities across the European Union and has been involved in considerable research projects. He is professor in the Department of Computing Science and has been supervised over 50 master science theses. He is also supervisor of doctoral students and responsible for cybersecurity and computing science study programs. Currently, Dr. Zelinka collaborates with Dr. Genaro Juárez on topics about robotics, intelligence, and complex systems. That's why we consider him an ally of SCOM. It is a great honor for us having him today to share his research and expertise in the field of swarm intelligence with the conference Swarm Intelligence from Quantum Circuits to Galactic Games. Please, let's welcome him with a strong round of applause.
Hello everybody. If you don't mind, I will stand up and will walk because I'm used to walk when I talk with students and audience. I will be nervous to sitting without any movement. First of all, I would like to thank to my colleagues for invitation and chance to speak here. And on the beginning, I would like to apologize for arbitrary typing errors or whatever, because I was flying 16 hours and the presentation has been done in the airplane during turbulences. So. That's the life of the adult academics, you know. Okay, so when I was talking with Genaro, he told me about I should have some lecture. It would be fine if I would have some lecture in 30-40 minutes. So I was thinking, oh wow, what shall I talk about in 30 minutes, 40 minutes, you know? This is just one conference paper focused on special one topic. So I decided to take some kind of overview of our previous experiments up to now. So presentation has a bombastic name, like from quantum circuits to galactic games, because I am going to discuss how we use the swarm intelligence in computer games. One of those you can just download from Google Play and play immediately here. I will talk about another applications we have did with the swarm intelligence. So let's start from the beginning. I'm from the Technical University of Ostrava. As already has been introduced, there is 7 faculties, and one of them, by the way, one of the most scientifically productive is Faculty of Computer Science, and we are located in Czech Republic, nearby border with Slovakia and Poland. People very often mix us, change us with Slovenia, which is something different. Also, I'm head of the group which has a poetic name Navy. The Navy is abbreviation of the Czech name Unconventional Algorithms and Computing, and I selected the abbreviation Navy for obvious reasons. Because when you are on the conference and everybody is sleeping and you stay, I'm from laboratory Navy, everybody wake up, and they pay attention up to the end of your presentation. So that's kind of trick. My group is focused on mainly on cybersecurity and various AI applications. And also I'm senior researcher on IT for Innovation, which is Czech National Supercomputing Center with supercomputers Karolina and the others. And since this January we established officially a new laboratory for quantum computing, and this year we should apply for real quantum hardware which will be delivered by the end of this year or the next year, and will be one of the 7 pieces located around Europe and will create kind of network of the quantum computers on supercomputing centers in Czech Republic and Europe. Well, agenda. Today's agenda is quite rich, but don't worry, I'm not going to avalanche you by details, because if you are interested in details, we can talk about details later, or you can take a look on the paper which are mentioned in the presentation. So all those areas I will discuss today briefly with the aim to show you that swarm intelligence is a very robust technology which can be used to solve almost arbitrary engineering problem. Each year when I start a course focused on bio-inspired algorithms, I usually say students, if you are able to define your problem as a problem of the minimization or maximization of some function which describe that problem, then you can solve arbitrary problem from any kind of engineering, while this minimization or optimizations leads to the solution. So let's take a look why the swarm intelligence and generally evolutionary computation is so cool and so good. I would like to start a little bit with a little humor. Classic engineering approach. When classic engineer is calculating something, so he's doing model, equations and so on, and then try to apply the solution. And sometimes it ends wrongly, The question is why? Our models in the past, even now, are very complex and with very high level of complexity and many details, many variables. Those variables influence each other, and part of models and so on. And in the past, engineers usually, when they met such complex models, they were under criticism because usually users wanted something simpler, which was more transparent, more easy to understand. So some reduction has been done. We got some model which is very nice, simple, everybody was happy. And when this model has been applied, and there is a lot of examples from engineering like Tahoma collapse, Tahoma bridge collapse, and other disasters, then when such model is applied to reality, then something wrong happened, explosions, collapses, and so on. And this is definitely not solution which we are interested in. So what we can do? One of the possible ways is use high quality mathematics approaches and highly educated engineers and so on. Or together with this, we can use the modern numerical algorithms like evolutionary computation or swarm intelligence. These two kind of areas are overlapping and basically are doing the same. Only philosophy which inspired their algorithmization is inspired by different part of nature. The evolutionary algorithm has a root in Darwinian theory of evolution, so that's why it's very often Charles Darwin mentioned as a father of evolutionary algorithms, while the Turing de facto has been a father of the evolutionary algorithms. And also I mentioned Czech priest Gregor Johann Mendel, who is father of genetics, and he did the same experiments as Darwin, while Darwin observed Mendel make real experiments and derive the mathematical models and functions which are used in genetics up to now. So these two guys contribute via Turing and Baricelli to the area of the modern evolutionary intelligence algorithms and swarm intelligence. And some of those names you already know, like Holland, Scheffel, Vogel, and so on. How much are you experienced with evolutionary algorithms? Okay, so briefly. You know what happens in nature. Parents have offsprings, better survive, worse individuals died. You know, this is so-called selection, and elitism. Elitism means only better survive. So that's basically described in this scheme. And this scheme represents evolutionary algorithms and in fact can be adopted for swarm intelligence too. So these algorithms are kind of iterative algorithms which are repeated in the loops and still improve solution based on the ideas from the Darwin, Mendel and the other scientists. Together with this, there is so-called swarm intelligence or swarm systems, and philosophy for those algorithms has not been taken from the classical population dynamics, but from the swarm systems which communicate and contain agents like ants, bees, fishes, birds, and so on. Those societies with many agents usually create a huge flock of agents who are communicating amongst themselves, and the communication, even simple, then cause that from the external observer point of view, the system behave like intelligent being. For example, ant, according to biologists, has only 45 instructions how to behave. But if you have many 100,000 ants in one ant colony, they behave like intelligent being and solve complex problems. I would like to mention Polish writer Stanisław Lem, who predicted swarm intelligence in 60s. That means about 30-40 years before it has been officially established or notified by scientists, by his novel Invictible, which is very fantastic science fiction and discuss one planet where is a living robotic insect which join together in the case of the danger, restore memory, strategies of the fight and start to fight with enemy. Very nice science fiction, but for me it's much more nicer that he predicted the swarm intelligence 30-40 years ago before standard science, which is perfect. This man was very excellent in forecasting, and Polish government in a communist era used him to forecast technological developments. So let's take a look on the swarm intelligence. As you see, as I told you, the swarm intelligence is taken from the nature or copied from the nature, and that means we have an algorithm which works with many agents. They communicate somehow simply like ants via pheromones, and their communication and their amount, that means number of individuals, then leads to the behavior which is simply very surprising and solve many problems. Those agents must be effective in find food and solve problems, otherwise they would not ever survive. And there are another part which are valid. So these are quite simple attributes of the swarm systems as we understand them. Today we can see swarm intelligence in biology domain, which is clear, insects, birds and so on. Then in computer science, where we can meet swarm intelligence in the domain of meta-heuristic optimizers, bio-inspired algorithms, and many other sub-areas which you already less or more know. And also in robotics, so we can use the swarm robots to solve some problems which can be solved only by high-level intelligence algorithms, as you will see later from animations. The swarm intelligence must exhibit those attributes like awareness, autonomy, solidarity, expandability, resiliency, and so on. And when those attributes are present in the swarm systems, we can say that this is swarm intelligence or swarm systems. Oops. Can you run please this animation? Just click on it. This is simulation of the artificial ants, and the authors of this animation put there the food. There will be kind of nest. Then the green part means they have to slow down, and the task is to find the shortest path, I mean from the time point of view, to take the food to the nest. And those artificial ants behave similarly like ants in the nature. They release pheromones which attract another ants to that path, And as a cumulating effect, we can see that during short time the path is generated without any central control, only via local communication between the agents. And if you put away this green zone, they very quickly restore the path and find the shortest path comparing to the previous one. So that's the demonstration how the ant colony, for example, works. And as we know today, ant colony is excellent for traveling salesman problem. As far as I know, do you know how many cities can be solved by ant colony optimization? I read in one literature that 10,000. So 10,000 factorial is number of possible, even nonsense combinations of the trajectories. So this is a huge number, and that can be solved by ant colony optimization in real time. So this is very powerful algorithm controlled by very simple primitive rule and contain only simple agents. So let's go to the examples. First, 1 year ago we tried to apply the swarm intelligence exactly self-organizing migrating algorithm which was improved from the past versions to create the quantum computing circuits. Everything has been done on IBM Qiskit environment, and the circuit was very simple. We just want to try whether the evolution or the swarm intelligence is able to construct the circuits which will do some simple operations. And we found that swarm intelligence logically has been able to construct the different circuits with the same functionality, and also we found the constructions which save 1 qubit, which was, according to our experts on quantum computing, quite interesting. So that was a very simple task, however very important, because we verified that intelligence can be used to design such kind of secrets. Today we are playing with Toffoli gate in his register programming shape, and we try to apply the swarm intelligence to synthesize a Toffoli gate in artificial way, and our aim or dream is to synthesize new gates based on the swarm intelligence application. It has been published in this paper if you would be interested to read details. There are some results. We evaluate those results for a number of simulations, cost function evaluations during the simulation with swarm systems, and how many times which secret has been generated, how many often appears one solution and another solution. So we made some kind of statistics about it. Another issue where you can apply the swarm systems is swarm robotics, which is quite obvious because the ants are simple robots. So one of our papers from the past, from my Vietnamese student who is now back as a PhD in Vietnam, was that kind of research where he applied the SOMA again on the swarm systems, and he simulated in the dynamical environment where was 5 obstacles and I think 4 or 5 robots. Their control so that they try to avoid themselves and obstacles. This diameter is basically diameter of the visibility, so that means if something went in, then robots see that obstacle or another robot and try to avoid collision. And the simulations are here. Please, can you run this simulation? So on this video, if they will start it, you will see how the robots are aiming to its target. So blue to blue, magenta to magenta, red to red target, and they try to avoid themselves and obstacles. Those trajectories has not been calculated a priori from the beginning to the end before the simulation. They were calculated in the running time online. So each step on its trajectory means one calculation step ahead. So that was kind of control. Can you please run this video? This video shows how the problem looks from the point of view of a robot. He's basically trying to capture its target and avoid obstacles which appears here like those hills. And why they appear and disappear, that's because he is moving around obstacles and leaving them. So when the robot registers obstacle or another robot, then there appears in that landscape kind of maximum, and because he's looking for the minimum, then he avoids, the robot avoids those local maximas. So again, whole the control problem has been kept like problem of optimization. There are another statistics and pictures where we try to visualize all possible simulations and trajectories together to see what was the complexity of the controlling and whether we repeated some trajectories or not, and if yes, then how densely. The same has been applied on the flying robots, where was the cost function measured distance to the target and to the obstacle, and its minimization step by step, and immediately checking the positions leads to the dynamics, which looks like this video. Please, can you run it? And those flying robots try to get those black dots as targets and avoid those balloons which represent obstacles. That was done in MATLAB environment. This guy made on this whole dissertation thesis with many details and simulation. These are only part of his presentations and simulations. And once more. So behind those trajectories is again swarm intelligence calculating each increment step by step. Another application was done with different algorithms in the area of so-called symbolic regression. Symbolic regression means that you apply the evolutionary computation or swarm intelligence, whatever, so that you don't optimize numerical parameter of your problem, but you define building block elements, we can call them programs or atoms, and say to evolutionary process or swarm intelligence, okay, they are building blocks, please join them together so that they will show some functionality, like amplifier, for example. And we try a lot of different simulations, and one of them was focused on finding on famous Santa Fe trail, which is this path, commands for the robot who move from the beginning to the end without leaving of the trajectory. If he left the trajectory, then his commands were wrong. So I will show you simulation. You will see that the robot will be yellow arrow and moving along the path, and when he met the gray spot, he started to sniff around, because there were conditions. If you met the gray square, just look around where you should go, because gray square is only for us to see how the path looks like. Otherwise, for the robot, those gray scale squares are normally white, and he see only one square ahead. So when he come, for example, here, he have no idea where to go. So he start to sniff around and taking decision. And that's the simulation and the result of one of the best simulation. We found better solutions than with genetic programming. We create our own algorithms called analytical programming, and comparing to genetic programming, analytical programming can be applied to arbitrary algorithm in arbitrary programming language. And tree representation of the program looks, for example, like this. So there is a series of the decision conditions and actions which should happen if then. And when you apply that iteratively on the robot, then he is then, according to those commands, moving along the trajectory. And when he met gray spot, start to take a decision where to go. Behind this winner, there was also many dead solutions, which looks like, for example, this. You know, they travel through the whole grid, so they were rejected as a wrong solutions. So if I say that swarm intelligence found these very nice solutions and better than Koza's solutions, then that it doesn't mean that it has been found on the beginning, just like this. You know, behind this result, a lot of calculations and computations, and the best solution has been represented here as a solution. But if you are able to do it in real time, and if you are able to get your results sooner than you need them, then you can use those approaches in real world applications. This is one of the oldest experiments which I am very proud of, because this experiment is very beautiful. We did it in 2003 in plasma reactor laboratory in Oxford, where we tested simulated annealing, differential evolution, and SOMA algorithm, which is swarm-based algorithm, on plasma reactor. Can you decrease the loudness, please? Thank you. Can you see this needle here? So that was plasma reactor, the needle measures state of the plasma, and there was 14 parameters which should be adjusted to get correct information from the internal box of the plasma reactor. It was done also by human, so the human hand tried to estimate those parameters, and then those three algorithms tried to estimate those parameters. Why this experiment is so nice? This is only one experiment I know and I ever met, which has been done on the real-time running system, which was black box. When we start these experiments, we ask physicists, please, do you have mathematical model we would like to play on the computer first? They said, no, we don't have mathematical model, just this plasma reactor. So we take it like a black box, and we play with this black box in real time. So when we apply possible solution on the input, plasma reactor make a reaction, change behavior, and give us output. And there was no chance go one step back and repeat that from the same conditions again to improve our simulation. So any input for the plasma reactor change its behavior. Despite the fact of this, we were able to find solutions during, anyway. There was so many possible combinations, control combinations, that if we would like to use brute force method, that means test them all and select the best one, regarding to speed of the hardware, it would take about 10 power 41 years. Our universe exists 10 power by 9 years. Because I'm here, experiment finished, so that was less than 10 power by 41 years. Can you guess how long it takes to get solution? 4 minutes. During 4 minutes, the swarm intelligence, including those evolutionary algorithms, found a solution which was repeatedly confirmed. So 4 minutes was enough, comparing to brute force and 10 power by 41 years. So that's why I like this experiment as a very nice demonstration that those algorithms are really applicable in the real life problems. Another issue which sounds quite science fiction. My colleague in Russia, Nikolai Kuznetsov and Gennady Leonov, unfortunately Gennady is passed away, they found so-called hidden chaos. Hidden chaos is a very specific kind of chaos and is somehow joined with René Thom's catastrophe, which is mathematical discipline. And this chaos can be visualized like attractors or bifurcation diagrams or just time series of unpredictable behavior. But if this kind of chaos appears in electronic devices, like this is Chua's secret, and his dynamical behavior is on this oscilloscope, we recorded, this is our own production, then if appears in that kind of device, then can lead to the events like this one. On the screen you can see the landing jet fighter Gripen, and look what happens just before he touched down. This is not only one video, I have more such videos with different airplanes. He simply start to make a waving and then crash like this, you know. And that's the result of the hidden chaos, which is very tricky, and if you get trapped in, then you have very big problems to leave it without any bad consequences. And we tried to use evolutionary computation to identify such kind of chaos inside even system, and we succeeded. So that's any other application how that kind of algorithms we use SOMA as well as differential evolution, so both algorithms, evolutionary and swarm intelligence based. This is another way how they can be applied on such exotic domain like chaotic behavior and collapses or disasters which are joined with this kind of behavior. Next issue. Because I'm working on the swarm cybersecurity, I was also solving problem whether it's possible to use swarm intelligence as a protector as well as the attacker. So we try to make some experiments in which we create the computer virus, which is based on the anti-colony optimization, And merging with the classical virus, we get a swarm virus which was able to move in the file system. Today it's able to move over the computer network, and it's based fully on the swarm intelligence principles. And this software is basically universal, so it can be used also as a defender. Just now we are negotiating with police to use this kind of system for some their activities. So this is also possible, to merge swarm systems with the malware or anti-malware system and create kind of robust swarm intelligence-based, for example, anti-malware. And that kind of virus has a different states, like here, infection, execution, which are typical for virus. Then we move forward, because we were interested, okay, if it's possible to create such virus, then definitely soon or later somebody come with this virus, and we need to know how it behaves, what we can record its behavior, how this behavior will looks like, and so on. So we try to map communication amongst the agents inside the swarm, and we got such kind of networks which looks like social networks, where each vertex represent one of those viruses and its importance for the communication of the swarm. And we got some conclusions reported in that paper. So it can be visualized as a social network of communication. And then, as a last experiment in that cybersecurity field, we try to merge it with neural network, and the result was like this. We got a swarm which is communicating among themselves, moving through the cyberspace. That means jumping from computer to computer or inside of file systems from file to file for simpler simulations, and also contain the neural network which is distributed through the swarm, and this neural network can serve like executor of the commands for whole swarm. So basically this is kind of swarm intelligence based cyber weapon which I'm also teaching in our lectures for cybersecurity. And this swarm has a lot of advantages and disadvantages. For example, if you kill all of them and only one survives, he's able to restore whole pack back. So it's like Greek Hydra from Greek mythology. So that's another application from swarm intelligence. As a bonus, I would like to show you before another application in cybersecurity. We also try to analyze malware via fractal images, and we simply take about 7 million samples from asset company, select to about 65,000 samples, and we create their counterparts in fractal geometry visualization, and we used artificial intelligence to make decisions whether this is goodware or malware. It has been published in a journal, Mathematics in Computer and Computers in Simulations, and we are able today to visualize malware as such pictures, and each malware is unique, and then deep learning is able to recognize those pictures, whether this is goodware or malware, with very quite high success ratio. But we are still doing some improvements. Back to swarm in malware. One of another applications is adaptive intrusion detection system training, where we use PSO, gray wolves, SOMA, and differential evolution to train adaptive intrusion detection system, so that the swarm intelligence has been simulating attacks, simulating various kinds of attacks on that intrusion detection system, and the systems try to adapt those attacks to be more and more robust, and that was captured in the time as a development and higher value, better reaction. So you can see that it converged to the one, so that means the system has been trained well. For that topic, there is a whole diploma thesis of my student, and if you will be interested, I can provide you with this thesis. It is in Czech, but it can be translated into English very, very easily. So the swarm intelligence can be used also for defense or for training of the defending systems. We have also one piece of hardware called Ixia Breakpoint, which simulates about 300,000 samples of malware and different network traffic, even malicious one. But this is just software solution. Let's go to the computer games. Do you know this game? Of course. So, my student, he was a fan for gaming, not me, because, you know, I'm old man and I played games in 90s, you know, so that was totally different graphics. But he was crazy for computer games, so he selected for his diploma thesis, okay, let's take a swarm intelligence and let's try to create a bot which will play in that game for us, you know. So he created a bot which was used for, I think, Terrans, if I'm not wrong, and these are screenshots from the game. Could you run this video, please? And then we made some experiments, record some simulations, and the bot works like this. Normally, you are building up some bases and pick up the minerals and so on, and expanding on the planet. But on the planet, there are another two races, Protoss, Terrans, and Zergs, if I'm not wrong. And when you met the enemy, you start to fight. And that bot was working like this. So when we took decision that we will find the enemy base, so the pack of the warriors start to search through the landscape of this planet, and that moment was moment of the swarm intelligence application, because if you take a look on the particle swarm, on the SOMA algorithm, they are working like this. They are searching on the landscape of possible solutions, in that case on the landscape of the planet, for the optimal path to the optimal solution. And the optimal solution was to find the enemy base. You know, when the base has been found or enemy unit has been met, then standard algorithms for finding came into activity and the swarm intelligence has been switched off. So the swarm intelligence worked on that game only as a search algorithm for enemy units or enemy base. And the cost function has been built so that if during our search enemy attacked our base, then the value of cost function has been turned upside down and the searching unit has been attracted back to the home base to protect it. So that's one application which also has been published in a journal and book chapters. Next, we published another chapters and papers about swarm intelligence in game sourcing, and one of them is about tic-tac-toe. If you take a look on the Google Play and just use this keyword, you will find application which you can find, install and play on a computer. Please can you run this video? And this simple application of the SOMA algorithm allows you to play tic-tac-toe against the SOMA algorithm. If you let parameters in setting as they are, it's very hard to win. But if you will cheat and with knowledge about algorithm will set those parameters not fair play, then you can win. But usually you don't win because the swarm intelligence is searching for the possible solutions where to put the green loop and where not. And if you don't pay 100% attention, you definitely lose. So that's the application which can be downloaded from the Google Play and you can play with it. When I talk about it on a MidSci conference 2015, during my speech I saw that students start to download the game, and at the end of the presentation they told me, this is not fair, we can't win. Because it's set, the algorithm is set for very good performance, but if you will play with the different strategies of the algorithm, with different parameters of the setting, then you can make the algorithm weak and you can win. But this is cheating. But who of us never cheat in game? You know? Next, exotic solution or application we try to use swarm intelligence, which is quite interesting in this case, was to compare ant colony optimization and human swarm system. We take a traveling salesman problem and we convert this traveling salesman problem into labyrinth. So you know traveling salesman problem. Cities are vertices, you know, and lines between vertices are roads. So we create kind of a labyrinth, you know, which was graphically visualized like this, and people had a chance to play this game and select which road they will select, they will follow to the next city, to next cross. And in each cross there were some credits, and the task was to pass as quickly as possible through all chambers or cross, if you wish, and select or pick up the most possible credits. When we use different versions of the anti-colonial optimization and the human players, we found that human players surprisingly are much more better. Not in speed, because anti-colonial optimization just run and stop. But humans, it take, for example, hour, 2 hours, 3 hours, because people simply said, oh, I'm lazy, I go for coffee and stop to play. But when you calculate the number of steps from the beginning to the end of the game, you found that the humans form is much more faster. Just note, the ant colony communicate via pheromones in this labyrinth. Humans have no pheromones, but humans see another players. So if I would be here, you would be here, I would see, aha, Pepe has much more better credits than me, so I will follow his path. That was kind of indirect communication between the players. And the question is, why the human players were so quick? What do you think? Any idea?
Quick in terms of time?
Pardon?
Quick, the human players quick in terms of time?
No. In terms of the number of the steps, calculation steps from the beginning of the game. Time was longer because they were slower than algorithms. You know, but they, during the game loop, they made a much more lower number of steps to find the shortest path rather than anti-colonial optimization.
I think that because in the beginning, there were a lot of players in the beginning of the game, and when they started to search the roads, they, like anti-colonies or sort, found the best solution.
Yes.
But it took time to players to get there.
But there was another attribute. Anti-colonial optimization algorithm contains agents which are very stupid. Only few, if 10. But the humans are clever, envious, you know, and so on. So when I see Pepe has more credit, oh hell, he can't have more than me, so I follow him and, you know, and try to dig out the more credits than he, you know. So the agents in the human crowd were much more intelligent agents. So I think that's the reason why they were better in the final result. But that was our experiment on so-called game sourcing. Game sourcing means mathematical problem is encoded into game, you play the game, and by playing of some kind of labyrinth, you are solving Traveling-Salzman problem, for example. Today we have a new 3D version, but we don't have people who would like to finish that problem, because students last time are somehow focused more to money rather than education. But anyway, we made a lot of statistics and comparisons, you know, to support our results in that paper or chapter of book. And at the end, where it can be used, that was just peak of the glacier. I forget to put their example where we used analytical programming as for the robot commands in order to get mathematical formulas for data streaming from robotic telescopes. Sorry for that, but we can discuss that later if you'll be interested. But at the end, I led one very nice experiment where the swarm intelligence or generally evolutionary algorithms, if you like, can be used. Scientists has been solved problem whether on the Earth-like planets, very heavy, can live some organisms. If yes, they have to have many legs. So the question is, can in evolution appears the creature which has 8 legs, and they made constructions and with different geometrical properties, you know, different length of the legs, junctions, and so on, and used genetic programming, genetic algorithms to find the best solution. And they found mechanical solution which would allow such creatures to live on the very heavy Earth-like planets. And this is artist say rendering demonstration how those creatures can look like, for example. But important is that evolution found the mechanical construction of their bodies. And if the simple evolutionary algorithms can do that, then nature during million years definitely too. So conclusion. As I told you, I give you warning on the beginning, 30-40 minutes is nothing, you know. That's only for 1 or 2 conference papers to explain them into some basics. So conclusion, I put there the questionnaire just for the reason, because there can be a lot of conclusions. For example, those algorithms can be applied in many engineering and scientific applications. They can be applied in design of different technical devices. For example, antenna for the deep space research for NASA probe. I don't know, 10, 15 years ago has been competition to design the antenna. So many engineers design nice antennas, as you know them, symmetric and so on. And then appears very terrible antenna which looks like as if somebody would, smash it by hand. And that was designed by evolutionary computation, and the antenna won the competition because it has the best parameters for the antennas. So you can use it for air-wing design. You can use it for electronic device design. You can use them for finding the suitable commands of the robots. Or even you can use, without any searching for some symbolic commands, just real-time driving of the devices like plasma reactor or whatever else. So these algorithms are very powerful and very useful, and I hope that this presentation gives you some kind of inspiration. And also I hope that after my 16 hours flight you understand my Chinglish. Chinglish means Czech English. And if not, sorry. And thank you for your attention. I definitely overstepped time. But if you want to discuss something, I'm here up to Tuesday with our embassy. Thank you. I'm quite nervous when people applaud me, because students normally don't do that.
Okay, thank you very much, Jelivan. This was a very wonderful talk with many interesting points. Please, if you have any question, please.
I have,
Okay.
the lady in the back. When nobody have questions, I usually say, everybody understand or nobody understand?
Allá atrás, y aquí en medio. No, de este lado. ¿También? Okay.
My question is that if a swarm is also use heuristic, so they can manage a little better all the problems that you mentioned that can have about the way it solves the problems.
Can you please repeat the question?
That if a swarm also use heuristics, so can approach to the human thinking?
Very good question. I answer you by question. I was talking about swarm intelligence, agents communicating among themselves. They, for external observer, they looks like intelligent being or pseudo-intelligent. On the other side, we have another kind of intelligence which we call brain. It's closed in the school, no flying agents, nothing like that. But, that's my hypothesis. Are you sure that your brain is not swarm intelligence? Forget that it's closed in the school. Forget that the neurons as agents are joined by synapses. This is just interpretation of the communication. So the neurons are units which process information, and synapses and their strength is kind of a communication channel. If you take this into more abstract level, then you will see swarm in your head. Many small neurons communicate among themselves. Each neuron has no idea that he exists. But 1 billion has idea, oh, I am. So my hypothesis is that there is only swarm intelligence, and because this interpretation or realization of this swarm intelligence is closed in one box, we say, oh, this is something different, this is neural network. If this is answer to your question.
I had a question there are certain models for certain types of problems, and my question is the swarm model was good for solving the protein prediction modeling, or is it was more for other kind of situations?
I think you mix two things together. One is algorithm, second is model. So the model whose optimization should lead to solutions should somehow describe the problem. This description should be done so that minimum or maximum of this function, its coordinates give you solution. And the algorithm is method which we use on the model. And then the question is, how powerful is this algorithm? Because not each algorithm is suitable for every problems. You know, there is so-called no free lunch theorem, which say that this class of algorithms is excellent for protein problem solution. This class of algorithms is excellent for traveling salesman, but they can't be used for that because performance will be very low. You know. So if I understand well your question, I would answer like this: different algorithms with different performances for different kind of tasks, and those tasks are represented by some mathematical model of plasma reactor, wing of the airplane, and so on, or folding of the protein in the 3D space.
Thank you.
Aquí de este lado, falta. Aquí en medio, por favor.
In my life, I found that the most killing questions are from people who start, sorry, I'm not professional in this, but I have a simple question.
Okay, this question is not quite related to your presentation, although I'm really more interested in your research. As far as I'm aware, you're researching on complex systems, right? But my question is that if you're researching on complex systems or on a more holistic view, or is it implicitly related to your works on computational intelligence?
That's a good question. I'm something between, something in between. I like the holistic approaches because it gives you a global view, you know, and I'm working also with computer intelligence. So, and even itself, computer intelligence can be very complex, you know. I hope I understand well your question.
Okay.
Hello. So you said there were algorithms that could resolve a problem in a amount of 4 minutes. You said. So I know there's some algorithms, some quantum algorithms that could solve problems that are so complex we cannot have any the time to solve them. So what happens when each agent has this quantum capability of maybe not executing, but retrieving that information from a quantum computer?
So
are we ready for that? Is that a problem for security? That's my question.
Okay, so you mean what would happen if we have a swarm system where each agent has a quantum computing capabilities,
yes,
or something like that? Yeah. Then God with us.
Yes.
Because today my colleague is working on post-quantum cryptography, and they are solving in their projects how to handle cryptography when the quantum computers will be really accessible and working. And I know that this is nightmare of the CIA, NSA, and all those services, because if they don't develop new method now, then when quantum computers comes, the encryption will be broken and we will see all secrets. But I think that's future, definitely it will come. But what kind of capabilities such phone will have, that will be terrifying, I think.
Thank you.
Okay.
I have a doubt. Is about the plasma. How is building? Is base of algorithm, or how is building the plasma? Reactor plasma?
Yeah, I know. I'm just trying to understand your question. That plasma reactor was not high temperature plasma. There was 300,000 volts, and low pressure, so that was that kind of plasma. I'm not physicist, you know. And these plasma reactors simulate the industrial plasma reactors which has been used at time for production of the semiconductors, you know. And the question was when to stop the plasma reactor to clean the chamber, you know, and start again process, but not soon, that would be expensive, not late, that would be expensive because we would produce the bad semiconductors. And that was measured by this probe in the plasma, and because the probe was needle, there was non-linear kind of field around it, and this non-linear field distorted use of a signal about state of plasma. So we were looking by these 14 signals to anti-noising signal, you know, to put away from the signal this distorting information. So that was main idea of this plasma reactor. Plasma wasn't million kelvins or so. No. But it was very sensitive to any light. So we were 3 weeks in the completely closed laboratory without windows.
My question is about the tic-tac-toe game. You showed to us about a video of a swarm algorithm to an agent player. So my question is, how hard is in training this swarm algorithm for the tic-tac-toe player, the agent player, sorry? And what is the strategy to training?
So first question was how it was trained?
Yeah.
There was no training. There was cost function which described all possible positions of green circle, which is soma, against your blue crosses. So when you put blue cross, the soma start to investigate around this cross, where is the most optimal put the green circle, and put it. When you add new blue cross, you change strategy and start to create a line. So this cost function in soma has been built so that it, in investigation where to put next green loop, was too functional. First, profit for myself, and second, stop you. So when this cost function saw that better is stop you than make a profit for me, that means made a chain of the green circles, then green circle was given to your blue cross line to stop you. So that was not training. That will be neural network, but this swarm system don't need training, just properly defined functional which described, say, profit or success of your strategy.
Okay.
It's described in this paper in details how the cost function has been built and this mathematical formula which leads to that kind of behavior.
Okay, thank you.
You're welcome.
Aquí hay otra.
Hi, I have a question about the cost factor that you talked in the start of the presentation about the waves, airwaves that are not getting the airplane. And I have a question about that because it's a solution about that. To completely eliminate that factor?
That's a good question, because you saw that secret called Chua's secret, because Leo Chua is famous Chinese physicist now living in US. By the way, his basement is full of nice French bottle of wines. And he is famous for not only for his Chua circuit, but also for his prediction of memory store, which is specific semiconductor element. And he basically created this electronic device, and you see how it was simple. And it produced chaotic behavior in certain parameter settings, in certain regimes, you know. And if you don't have exact full mathematical model of this device, you can never predict it, you know. And now imagine, beside this simple electronic device, full control system of airplane. Thousands of elements, you know, and different dynamical regimes. You never know under which conditions it starts to behave crazy. So that's the topic, you know, that's the problem, whether we are able to at least by evolutionary computation or swarm intelligence, locate in the model possible threats that there can be kind of hidden chaos. Hidden because each chaotic attractor has a domain of attraction. That means if the chaotic attractor is like this, domain of attraction can be like this, and I start iterate from here and it will be attracted to the attractor and it's there forever. So you can very easily locate in this domain of attraction, aha, so there is probably attractor. But the hidden chaos means this attractor has such kind of basin of attraction, very tiny. So to hit it is probably unlikely, but when you hit it, you are in hell.
Thank you.
You're welcome. At least these two Russian guys established this term and developed a theory about it, and they are very good mathematicians.
Any other question? Gracias.
Hi. Speaking of profit and greedy students, I have a question about, is swarm intelligence, is it able to be applied on finance or economics in some way?
Definitely.
And how? How?
Definitely. So if you would like to make money, then let me think. Stock exchange is the dynamical environment where the millions agents, that means people and investors, put their money, and start to speculate and blah blah blah. All this influence together, and as a result, you can see some cure from the stock exchange as they are going up, down, and so on. And sometimes those time series are chaotic, but sometimes not. And you can find, for example, fractals in that time series which are called Elliott waves. Elliott waves are specific object which has fractal nature for certain reasons. And when you've met them, you can say, okay, so Elliott wave is here, so I must sell money, otherwise after fifth vertex it go down. I lost money because I didn't believe this theory once, and I lost 10,000 Czech crowns. Because the Elliott wave appears in my bank not in minute movements, but in daily movements, and it's very unlikely. So I said, okay, this is not a real wave in daily movements. And next morning I was poor for 10,000 Czech crowns, But back to topic. You can make a cost function which will identify those Elliott waves, for example, in the time series. Speculators on the stock exchange are doing this by different tools. They really identify whether there is flag, triangle, or Elliott waves, and based on the statistical experiences with those shapes, they take decision whether it's better to sell or buy. So this is normally used together with neural networks. And also swarm intelligence can be used to better train your neural networks or design their structure, because we use swarm intelligence algorithms to design neural network structure, and the structure was terrible. It doesn't look like normal technical neural network which has many inputs and then fully connected layers and output. The inputs were even into outputs connected, and the network was working perfectly. But from the structural point of view, network looks like natural product. So that means the swarm intelligence don't care about our ideas how, for example, networks should look like. It simply looks like in nature. It's looking for such solution, such connection which is working. So you can use it like this. Design your networks and then train networks to predict, or make a hybrid system where the network will be analyzing time series and the swarm intelligence also will be looking for some anomalies and then give you warnings. And some kind of decision system can tell you, okay, with very high probability you should sell it.
Okay, thank you.
You're welcome. By the way, my Vietnamese student, he's using those things for his forecasting of stock exchange. And I asked him, okay, and how much did you earn? Where is your BMW on the parking place, and he told me, oh, I invest $300 and now I have 5,000.
Okay, the last question, please.
Thank you for the talk, and also I would like to ask which cases or situations are the most difficult to, where you can use the swarm algorithm?
Once more, please. Which situations were more difficult for what?
To use the swarm algorithms.
Look, I think the bottleneck in those algorithms is how many cost function evaluations the algorithms in general need to get solution, and the most important is how long time take one cost function evaluation. One cost function evaluation means I put the individual from the population into model, and model give me feedback whether it's good solution or not. If this take 1 millisecond or nanosecond, perfect. But if that take 1 hour, then you will wait month or year for result. So important is to be sure that your algorithm which you are using for a given problem is suitable for the given problem, is able to, under specific setting, like tic-tac-toe, during a few cost function evaluations reach results. There is no cookbook for this. There are general experiences, statistical evaluations, and today the community know that, okay, differential evaluation is perfect, very quick, very powerful, and the most powerful algorithm of all. But I've found the problems where the summa, for example, was all the same quality of the performance like differential evaluation. This is no Fermat theorem. So you must be aware about cost function evaluation time and the number of possible cost function evaluations in average for a given algorithm and a given problem.
Thank you.
You're welcome.
Okay, I will take advantage of my position. I have 2 questions only for you. The first question is, how can you measure the swarm intelligence? Is here some taxonomy?
Measure. When we work with this, we measure its performance only by cost function evaluations. Because I met sometimes students or people who, even today, they use time. This is nonsense. Yeah. Because if I use my computer, your computer, supercomputer, time will be different for all computers. Yeah. But if on those 3 computers will be the same number of cost function evaluations, then algorithm is good on all 3 computers. So we use only number of cost function evaluations to measure performance of the swarm intelligence algorithms, even those evolutionary computations.
The second question is, looking at these algorithms, what is your better impression to use? A chaotic system or a complex system? What is more powerful?
For what use?
To use in these algorithms.
You mean employ them into algorithm or use algorithms
yes.
to solve them?
No, and only one algorithm to, for example, solve a problem of optimization. What is better, the chaotic or a complex system?
That's a very tricky question because chaotic systems can be complex, or simple system can exhibit complex behavior. And for example, we produced paper 2 years ago in information sciences, I think, and we employ the chaotic dynamics into evolutionary computation, into swarm intelligence. So we throw away randomness and put there chaotic systems. And chaotic systems are not chaotic. They have a very long period of chaoticity, but have specific attributes comparing to randomness. And the performance, based on statistic evaluation, performance of those algorithms increase. Statistically significantly increase. So the chaotic dynamic inside, instead of random, improve the performance of the algorithms. And on the other side, to answer your question, at least I hope so, we also publish paper or series of papers where we try to analyze the behavior of the individuals in the swarm as the social network. So when they create offspring, successful offsprings, or found better solution, they were judged like successful offspring, And in this way, we record the communication amongst them, and we got kind of social network which developed in time. And we took some attributes from this social network as a feedback to the algorithm to improve its performance, and again, it improved its performance.
Okay. So Ivan, thank you very much for this very nice talk. And Ivan, I don't know.
I thank you for your wonderful audience. You survived so long time with me, you.
Thank you, Dr. So, in the name of SCOM, please receive this gift as a token from Mexico.
Thank you very much.
Whenever you're welcome, whenever you welcome back.
Oh, super.
A lot of applause. This is your size. It is.
When I come back, first day I will dress it on my body and will walk along the department, you know. And say, boss, hey boss, I have a small contract there, you know.
Anyway, if you want a picture or some particular question with Ivan, please feel free to close to him. Thank you.
I can dress it for picture if you like.
This is a Mexican souvenir.